Now, this next topic is the crossed Claisen condensation. This is going to be a reaction of two different esters through Claisen. Now, a well thought out crossed Claisen condensation will give you one predictable beta-keto ester. But if your reaction is not well thought out, a crossed Claisen condensation can actually create quite a mess of products. So in this reaction that's shown on the screen here, we've chosen one ester that does not have any alpha protons. So this one cannot be turned into an enolate. And then our other ester does have alpha protons. So this ester is going to be our enolate, and you can see it here in our product. And it is going to attack the other ester, which is going to give us the rest of our product. And this bond in between them is the one that we're going to make through the Claisen condensation. So again, you really only want to do a crossed Claisen when only one ester has alpha hydrogens present. So good examples of esters that do not have alpha hydrogens are here below. You could have a carbonate diester here. You could have an ester made from an aldehyde, or made from formic acid rather. You can have an ester that has a quaternary carbon, or you could have a benzoic acid derived ester. None of these have alpha hydrogens, so these would all make good target esters. They're going to be our electrophiles. So there is one situation in which you could have an ester that would not be able to make an enolate that could proceed forward in a Claisen condensation. And this molecule here is a good example of that. So it only has one alpha hydrogen, which means that it can actually form an enolate. If we were to add in ethoxide, we could deprotonate that and form an enolate, and then we could create our beta-keto ester. But remember that the driving force for the Claisen condensation is that before you add in your aqueous acid workup, you are also going to create an equivalent of ethanol by pulling off an alpha hydrogen from between the two carbonyls. If you do not have another alpha hydrogen there, we actually cannot create that ethanol, and that destroys our driving force for the reaction. So this reaction is unlikely to proceed in the way that it's written out here. But one way that you could make a reaction like this occur would be to use a really strong base, such as LDA. If you introduce LDA to this ester, it is going to turn every single one of these ester molecules into an enolate, which means you could then add in a target molecule, such as benzoyl chloride. Now what that's going to do is give us a beta-keto ester, and we wouldn't have to worry about a driving force because LDA already did all the hard work of creating an enolate and pushing the equilibrium in the direction of the enolate. So our driving force becomes using up this much more reactive molecule to create the beta-keto ester. So this brings us to another type of reaction that can create beta-keto carbonyl compounds. So if you were to take a ketone and add in a strong base, such as sodium azonide, remember this is going to have an NH2 with a negative charge. This is a strong base. It is perfectly capable of creating an enolate off of this ketone. So we can create our enolate, add in an ester, and create a beta-keto compound. Now this is a really strong base, and so it's not going to necessarily create the thermodynamic enolate. It's probably going to create the kinetic enolate and just get the reaction done more quickly. Another example would be if you added in a ketone and then added in your weaker alkoxide base, you could create an enolate. and then add in something that is much more reactive that does not have alpha protons, and you could get it to react, and you could keep forming the enolate in this equilibrium and create some more complex molecules. So let's do a practice problem here. This one is actually a really interesting problem because we have sodium ethoxide here that matches our ester. That tells us that we're going to have an enolate situation here. But we also have several different alpha hydrogens that we have to consider before we can move forward in this reaction. So we have one on the end of the molecule. We'll call it HA. And then we have HB, which is just inside the ketone. And we also have HC. Now, hopefully you recall that alpha protons that are alpha to an ester are less acidic. So that means that HC is not going to be one of our options here. Our only choices are between HA and HB. And which one we use is going to come down to a couple different things here. The first thing that you have to consider is this is not a strong base. Sodium ethoxide is a weaker base. That means we're going to want to create the thermodynamic enolate, the one that's more stable, because we're going to be in that equilibrium. And you also have to consider what your product would be, what your outcome is going to look like. We know that this is going to be an intramolecular reaction, so we're going to create a cyclic structure. And we also hopefully recall that 6-membered rings are kind of the golden standard here. That's the best possible outcome. The next best possible outcome would be a 5-membered ring. And after that would be a 7-membered ring. So you have to think about how big your products would be. If we were to pull off HA, that would make our enolate over here. And it would be a 1, 2, 3, 4, 5, 6, 7-membered ring. So that's what would happen if we pulled off HA. If we pull off HB, our enolate would be on that 3rd carbon in from the left, and that would give us a 1, 2, 3, 4, 5-membered ring. So that's 1 vote for HB. Also, if we pull off proton B, we're going to end up with the more stable enolate because we're going to have a more substituted alkene. So let's look at that in detail here. So here's our enolate if we were to pull off proton B. Remember that this has a resonance form, which features an alkene. This alkene is more substituted than the alkene that would result from pulling off HA. So that's another reason that HB is going to be our preferred enolate. So let's go through the rest of this reaction here. We're going to erase our resonance forms to give us a cleaner slate here. So our enolate is going to attack our ester, and that's going to give us a cyclic compound. We already did our carbon counting here. We know this is going to be a 5-membered ring. 1, 2, 3, 4, 5. So you don't have to keep numbering your rings and such, but if it helps you, that's something I definitely want you to keep doing. So carbon 1 is going to have this ketone sticking off of it, so I'm going to put that back on there. Carbon 5 is going to have an O- from our carbonyl and an ethoxide group. So that O- is going to reform the pi bond. We kick out ethoxide, and we have a beta dicarbonyl compound. Now, I'm not going to make you go through that extra step of pulling off that proton, but do remember that that occurs here. That is part of the driving force. And this is our final product.